In this lesson, we're going to start discussing learning target number 6, describing acids and bases, focusing on the Arrhenius theory in this lesson. We'll also explain the pH scale and factors that affect it, along with neutralization reactions. As a quick reminder, let's go over the points of the Arrhenius theory. It states that an acid is a substance that produces hydrogen ions, or H1 pluses, when they're put in water. Here's an example of an ionization equation that we were writing in Unit 2, where we have hydrochloric acid falling apart into H plus aqueous and Cl1 minus aqueous. The Arrhenius theory describes bases as any substance that produces hydroxide ions, or OH1 minuses, when dissolved in water. And here's the ionization equation showing sodium hydroxide performing that ionization. We also describe strong acids and bases as ionizing or dissociating 100% of the time, and weak acids and bases having a low percent ionization. How acidic or basic a solution is described using the pH scale. The P actually is a Greek letter that stands for strength, so literally pH means the strength of hydrogen ions in solution. This scale is based on the molar concentration of H1+. The pH scale is logarithmic, which means that each increment on the pH scale goes up by a power of 10. Now it's a little bit of a strange scale. We'll go more into how it was constructed when you take grade 12 chemistry. If you have a solution that has a pH of 7, that's defined as being neutral. Less than 7 is acidic, and greater than 7 is basic. Now most people think the pH scale goes from 0 to 14, but it does go on in both directions. So if you have an extremely acidic solution, it can have a negative pH, or an extremely basic solution can be over 14. Now one misconception that people have is that the pH scale describes how strong an acid or a base is. And the further you get away from 7, the stronger the acid is. But check out the labels on these diagrams. Between 7 and 4 is labeled as slightly acidic, not weak acid. That's a different term. Slightly acidic means that it is corrosive, but it's not terribly dangerous. If you go below a pH of 4, then it's described as being very acidic. This means that it's highly corrosive and you need to definitely wear safety equipment and handle it carefully. Now the pH of an acid is affected by its strength, but also the concentration of the acid affects the pH as well. The stronger the acid is, the more it ionizes, which increases the H plus concentration in the solution, and it lowers the pH. Have a look at these two beakers here. Here I take 3 molecules of acid and put it into a beaker of water. If each of these molecules of acid ionize into H pluses and A1 minuses, then I have 100% ionization. A high ionization rate means I have a strong acid. If I look at this beaker, I have the 3 acid molecules as well, but only 1 out of 3 of them ionize. That's 33%. So this is classified as a weak acid. Because the strong acid has more H1 pluses in the same volume, it will have a lower pH than my weak acid. But this is not the only thing that determines the pH of the solution. the more concentrated the acid, or the more HAs I put into the beaker, the more acid per unit water, which increases the H plus concentration and also lowers the pH. Have a look and compare these two beakers. They're both strong acids. Here I throw in 3 HAs and they all ionize. Here I throw in 9 HAs and they all ionize. Both beakers have 100% ionization and they're both strong. But because I'm throwing in 9 acid molecules here, I'm going to have more H pluses in this container. This gives beaker 3 a lower pH than beaker 1, even though they have the same strength. Here you can compare beaker 2 and beaker 4 and see the same effect. They're both weak acids with only 33% ionization. Only 1 out of 3 acids fall apart. The difference between these two beakers is the concentration. Here I've put in a dilute solution, 3 HAs, compared to a concentrated solution, 9 HAs. Here I have 3 H pluses produced. That gives me a lower pH than the 1 H plus produced in beaker number 2. Now hold on a minute. Did you notice in beaker 1 and in beaker 4 they both have 3 H pluses made? Because the pH scale is based on the concentration of the H plus ions in the solution, beaker 1 and beaker 4 would have the same pH. In beaker 1 we have a strong acid with a low concentration. It's described as being dilute, having the same concentration as a weak acid that is concentrated. It is possible to set this up. What you have to do is have your strong acid that ionizes more at a more dilute concentration in order for the two solutions to be the same pH. Let's jump back up to the pH scale here. Let's say you have a beaker of an unknown solution and you test it and it's pH 5. Could you say it's a weak acid? That's only one possibility. It could be a weak acid. It could have a pH 5 because it has a low ionization. But it could also be a strong acid that's been diluted. It has 100% ionization, but because there's so few acid particles in the beaker, it doesn't make a really high concentration of H1+. Before we go on to neutralization reactions, let's return to this logarithmic bit on the pH scale. If you have two solutions, one with a pH of 5 and one with a pH of 4, the pH 4 is more acidic than pH 5. But because it's a full increment on the pH scale, it's not just a little bit more acidic, it's 10 times more acidic. It also makes it 10 times more corrosive and 10 times more dangerous. Now if we're comparing two solutions, say pH 5 and pH 3, because it's 2 increments difference, the acid that's pH 3 is 100 times more acidic and dangerous than the pH 5. Using stoichiometry, we can predict the amounts needed to completely neutralize an acid or base. When we mix them in stoichiometric ratios so that there's no reactants left over, this is known as the equivalence point in the reaction. Remember that an Arrhenius neutralization reaction is represented by this general equation. When you react an acid and a base together, you get a salt and water made. This is a double displacement neutralization reaction. Let's try out a stoichiometry example. Example 1 asks us what volume of magnesium hydroxide is required to neutralize a sample of nitric acid. Let's first start by writing a balanced chemical equation. This is going to be a double displacement, so my magnesium is going to go with my nitrate, and my hydrogen is going to go with a hydroxide to make water. Remember, whenever you're doing a neutralization reaction, just write down water. I know I've got an extra H floating around. It will come out when I balance this equation. I need to put a 2 here to balance my nitrates, and then I need a 2 here to balance my oxygens and my hydrogens. And I'm just going to organize my numbers in the chart below. Because I have complete information about my nitric acid solution, the volume I used and the concentration, I can use C equals N over V to find the moles of nitric acid I used. Rearranged, it's going to be the concentration times the volume in liters will give me moles. If I convert that into magnesium hydroxide, I have to times by a 1 over 2 mole ratio. That gives me 0.0625 moles of MgOH2. Now the question wants me to change this amount into a volume of 0.820 mole per liter of magnesium hydroxide. I'm going to take my moles and do some more math work over here. Because this is a solution, I'm going to use C equals N over V again. I already know the moles and the concentration. I rearrange this equation for volume, and I get 0.076219. Now that will be in liters. Looking at my SIGDIGs, the 250 mils only has 2. And if I want to, I can convert my final answer into milliliters by multiplying it by 1,000. So in order to neutralize 250 mils of my half-molar nitric acid solution, I need to add 76 mils of my base sample. Scientists frequently have acids and bases of unknown concentration, and they need to identify them. They achieve this by performing a controlled neutralization reaction. This lab technique is known as an acid-base titration. You accurately keep track of how much of the opposite reactant is needed to reach the equivalence point. Then you use stoichiometry to find the unknown concentration. Because the concentration of one of the chemicals is unknown, indicators are often used to determine when to stop adding reactants. When you stop, this is known as the end point in the titration. We often aim to add 1 drop of the titrant to change the indicator's color. This ensures that the endpoint when we stop adding the reactants is equal to the equivalence point when the acid and the base have completely stoichiometrically neutralized. This gives us a very accurate titration. Special glassware is used to measure the reactants. Have a look on page 468 to 469 on how to perform a titration. Example 2 shows the calculation process after the titration data has been gathered. It's a regular stoich question. Start by writing a balanced chemical equation. Here we're reacting hydrochloric acid with an unknown concentration with sodium hydroxide. We're going to do a double displacement neutralization reaction. I used 25 mils of my HCl, but I don't know what the concentration was. In the titration, it took 63.5 milliliters of 0.725 mole per liter sodium hydroxide in order to neutralize my acid. This is all the information that I need to find the concentration. Because I have complete information about this solution, the concentration and the volume, I can use C equals N over V to find the moles of sodium hydroxide used. If I take the concentration times the volume in liters, that will get me moles. To convert into HCl, I need to times by a mole ratio. In this case, it's 1 to 1. In order to answer the question, I need to use C equals N over V again. There's the moles of acid that was neutralized, and I'm going to convert the volume 25 mils into liters in order to sub it in for V. Looking at my original numbers in the question, they each have 3 sigdigs. So I'm going to round my concentration to 1.84 mole per liter of HCl. Try out the neutralization stoichiometry questions listed on your assignment cover sheet.